Okay, so we have, so today is week 10. I'm going to just cover a couple topics today. It's less calculations, a little bit more conceptual. Shouldn't be too bad. And then next week we will spend, will be devoted to review. And then the week after that will be the final exam. Okay, so we got week 10. Oh, sorry, this is
This is the last lecture?
no. Well, I guess the last lecture of new stuff. Okay, so so this will be yeah, week 11. There is a quiz. Okay, so next week will be a review, and there is a quiz 8, and that will just cover the stuff from today's lecture. Okay, and then week 12. So week 10 is today. Next week is review. Week 12 is the final exam. Okay. As far as homework for this week goes, it's pretty light, but the your homework from the book is light. Okay, so so this week there's going to be a little homework from the book. Just a few questions, okay? But I have uploaded a practice final exam. Okay. And so your responsibility this week is to work through the practice final. That's going to be your homework, all right? Because next week during review, I'm going to go through all of the answers for the practice final. Okay. And so if you have, you know, your time, you know, I'm not going to check to see if you've done your homework, but it will be much more meaningful and a better review if you've actually tried out the homework problems yourself, and you'll be aware of what areas you are strong in and what areas you are deficient in. Okay, and that will make the review time more meaningful. Okay, and then the week after that will be the final exam. So so that should be it. Next week also there is teacher evaluations. So I appreciate you coming and giving me good reviews. But you know, of course, and then you know, if you've enjoyed the course, you know, please leave me a review at Rate My Professors or you know, those types of sites. So that's you know, I think your reviews there help students choose classes in the future, other students choosing classes, and so it's always nice for me when students enroll in my class. So okay, all right. Well, today let's cover the stuff, and yeah, we'll see how much we can get through, or how quickly we can get through it. So. Okay, so I wanted to talk a little bit more about hypothesis testing and kind of the conclusions that we make. Okay, so in hypothesis testing, okay, so as far as conclusions go, we really only have two conclusions that we can make. Okay, so one is if the p-value, so you do your calculations, right? You get your standard error, you get your test statistic, you look up your test statistic, and you get a p-value. Okay, and either the p-value is going to be larger or smaller than some value alpha. So if the p-value is alpha, what does this mean? If the p-value is greater than alpha, this means we do not reject the null hypothesis. What do we say about the alternative? Yeah, we would say we do not accept the alternative. And then regarding evidence, do we say we have or do not have evidence? Yeah, we do not have evidence. That the null hypothesis is false, okay? But could the null hypothesis be false?
Yes.
Yeah, it's just that at this point, we don't have enough evidence to say that it is false, okay? Okay. But the null could be false. I'm using a thicker pen. Is it way better? Okay. Sorry. It's just at the end of the quarter, finally got the pro version, and now I have thicker pens. So okay, well, in the future I'll be sure to use the fat pen. Okay. All right, and then on the other hand, we have if the p-value is less than alpha, basically we just change all of these nots, get rid of them, right? So if the p-value is less than alpha, we do reject the null. And we do accept the alternative. We do have evidence. That the null hypothesis is false. Okay. And then we would say, but in this case, but the null hypothesis could be true. Okay. But our data leads us to believe that it is false. Okay, so this is what we have. And so let's talk about this choice of alpha, the significance level. Okay. And I'm hoping this is kind of like review, and we're already familiar with all of this, right? But it's just we're writing it all down. This is what we've got to know. Okay. Well, okay. Well, let me just remind you what our p-value is. Okay. So the p-value again is the probability of observing our data or something more extreme if the null hypothesis were true. Okay, the p-value is the probability of observing our data or something more extreme if the null hypothesis were true. Okay, and so large p-values mean that, you know, our data is likely to happen just from random chance. Just from random chance, while the null hypothesis is true. Okay, so that's why when our p-value is greater than alpha or p-value is large, we would say we don't have evidence against the null. We don't reject the null. Okay, and on the other hand, small p-values mean that our data is unlikely to happen, or indicates unlikely to happen from random chance alone. While the null hypothesis is true. Okay, and all right, and so the alpha, our choice of alpha is, the alpha is our significance level. The default choice for alpha is 5%. .05, okay, and this, our choice of alpha reflects to a degree how willing we are to be wrong, okay, and how willing we are to be wrong in a specific way, okay, so a willingness to make a particular mistake. Okay, and this particular mistake is called the type 1 error. Okay, and so, you know, when statistics was being developed as kind of a subject and people were thinking of stuff and discovering things, we didn't have names for these errors, and so they creatively named them type 1 error, and then there's another kind of mistake, and they called that one the type 2 error, because that was as creative as they were feeling. Today we kind of developed better names for these things, and so the type 1 error is often known as the false positive, okay? Okay, but false positive is often reserved for certain contexts, but I would say a type 1 error is generally known as the false positive. And then there's the other error, the type 2 error, and we'll talk about that, and that would be the false negative, but that's coming up. Okay, so what exactly is a type 1 error, okay? So a type 1 error is this, okay? We make the choice, or we make the conclusion that the null hypothesis, or we make the conclusion to reject the null hypothesis. Sorry. We make the conclusion to reject the null hypothesis. But it is an error because in reality, the null hypothesis is true, okay? Okay, and so, you know, so this is an error. So this conclusion is a mistake. Okay, and alpha is equal to the probability that we would commit a type 1 error. Okay. And so you might say, well, that doesn't sound good. I don't want to commit errors. Why would I choose alpha to be 5%? Why don't I just choose alpha to be 1% or like 1 in 1,000% or 0%? Okay? Well, the converse is you could say, yeah, no, that's fine. We can choose, and I'll give a kind of an example, because right now this is all kind of in theoretical land and it might not make any sense. If we choose to decrease alpha, okay, decrease alpha to reduce the risk of a type 1 error, okay, we will increase the risk of another kind of error, the type 2 error. Okay, and so a type 2 error is the other kind of mistake. Okay, we make the conclusion not to reject the null hypothesis, okay, but it's a mistake because in reality, what? If it's a mistake to not reject the null hypothesis, in reality, the null hypothesis is false. Okay, so this is a mistake. And so that's a type 2 error. Okay, and then we would say beta is the probability of committing a type 2 error. So alpha is the probability of a type 1 error, and beta is the probability of a type 2 error. Okay, so alpha is kind of, if you're trying to remember like what is what, okay, so what's the first letter of the alphabet? A, right? Okay, so first letter of the alphabet, not iced. First letter of the alphabet is A. Okay, and then and the Greek analog to A is alpha. Okay, so alpha is A. So actually it probably makes more sense to use the lowercase letters, because alpha kind of looks like a lowercase a. All right, and then this, as far as type 2 error, the second letter is B. Thank you. Glad we have established that. Okay, and then so B looks kind of like the Greek letter beta. Okay, and actually that's where we get the word alphabet, is from sticking together alpha and beta, and we get alpha. Oh yeah, right. Okay, so alpha beta. Okay, alphabet, and that's what we have there. Okay, so that's your type 1 error and type 2 error, alpha and beta. It's the probability of a type 1 error and probability of a type 2 error. So again, we said type 1 error can also be called the false positive. And type 2 error could be called the false negative, okay? So, can I flip to the next slide, or are we still writing? We're good? Okay. So, you know, I mean, ideally, if the null hypothesis is true, our conclusion would be what? So if in reality the null hypothesis is true, at the end of our test we should, what, reject or not reject the null? Our conclusion would be, do not reject the null, because it's true, right? Why would we want to reject something true? Okay? And if the null hypothesis is false, ideally our conclusion would be to reject the null, okay? But the mistakes are, if the null hypothesis is true, you know, we conclude, our conclusion to reject the null, this is a type 1 error. And if the null hypothesis is false, our conclusion, do not reject the null, that is a type 2 error. Okay, so we have ideal conclusions and the mistakes, and we can make a little grid table if we want to. So we'll put our conclusion over here. And then we'll do the reality. So the conclusion could be reject the null or do not reject. And then the reality is the null is true or the null is false. Okay. So null is true, and we end up rejecting the null. What is this? Ideal, correct decision, type 1 or type 2 error? This is a type 1 error. Okay. The null is true, and we choose not to reject the null. Type 1, type 2, or correct decision? Correct decision. Okay. In reality, the null is false. Our conclusion is to reject the null. What's that? This is the correct decision. Bless you. And this last box has a type 2 error. Okay. So let's try an example here and talk about why we might want large alphas or small alphas, okay? So, you know, often we just kind of say like use alpha equal to 5%, but in certain circumstances, we might choose to use a larger alpha or choose to use a smaller alpha, okay? So, you know, here we're not going to have any math involved, but conceptually, let's talk about, you know, what would happen in kind of a, so imagine you're in the courtroom and we have a criminal trial. Okay, all right, and so as far as the trial goes, all right, the defendant is always presumed to be what? Innocent until proven guilty, right? That's how our justice system is set up, and it's a good thing. And so then the null hypothesis, because we're going to assume that the defendant is innocent until there's enough evidence to convince us otherwise, or convince the jury otherwise, the null hypothesis is what we're going to assume to be true, and that's going to be that the defendant is innocent. Okay, so we presume this to be true. Until the evidence convinces us otherwise. Okay, and then so the alternative would be what? The defendant is guilty. Okay, or not innocent would mean guilty. Okay, all right, and so as far and then so the prosecution presents evidence, right? The defense tries to explain it away, explain whatever evidence the prosecution brings forth, and then so we'll say the prosecution presents evidence. Okay, and then as far as the conclusions go, so the jury can make one of two conclusions. When they read off, we, the jury, find blah, 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 what do they say? So they say we find the defendant guilty. Okay, so either the conclusion is defendant is found guilty, and so this would be equivalent to what? Are we rejecting or not rejecting the null? We are rejecting the null hypothesis that the defendant is innocent, right? Okay, and then the other, if they don't say the defendant is guilty, they would say the defendant is. No, they never say the defendant is innocent. They say the defendant is not guilty. Okay, and there's an important distinction there. Okay. Okay, because the jury never says we find the defendant innocent. They would never say that. They would say we find the defendant not guilty. And there is a distinction between not guilty and innocent, because not guilty just means there wasn't enough evidence. It doesn't prove that the defendant is innocent. It just means there wasn't enough evidence to say guilty. So the defendant is not guilty. This is do not reject the null. Okay, and so that's why I say don't ever write we accept the null. Okay, because the jury never says innocent. Okay, because that would be saying accept the null. Okay, and that's just not how it works. Okay, there is an important distinction between innocent and not guilty, and so the jury never says innocent. Okay, innocent is not the same as not guilty. Okay, and so I know a lot of times students complain about how we have to write all of these conclusions with all of these double negatives, and like we don't have evidence that it's not this thing or something like that. That it's because of this. Okay, we can't say this. Okay, so in ideal situations, okay, so ideally, if the defendant is guilty, or if the defendant is innocent, we'll say if the defendant is innocent, the jury concludes what? Yeah, jury says not guilty. And that would be null hypothesis true, do not reject the null, right?
The null being the innocent until proven guilty, that's the null.
No, the null is the defendant is innocent. The way we've set up our courts to say we presume innocence until proven guilty places innocence as the null hypothesis. Okay, so null hypothesis true, and then we do not reject the null. So that's ideal situation. Ideally, if the defendant is guilty, the jury says what? The jury says guilty. So null hypothesis is false, and we choose to reject the null. Okay, so those are the ideal situations. Okay, so let's, can I flip to the next page? Looks like some of you are still writing. Okay, and then, but because no one knows everything, all right, and evidence can be destroyed and things of that nature, or, you know, maybe people make mistakes, really. I mean, that's just a fact of life. The court system is not perfect, right? And so there are mistakes. So the ideal situation, if the defendant is innocent, they're found not guilty. If the defendant is guilty, they're found guilty, okay? Mistakes, all right. So the mistakes is the defendant is guilty, but the jury says not guilty. Okay, so this is one type of mistake. And then the other type of mistake is the defendant is innocent and the jury says guilty. Okay? So one of these is a type 1 error and the other one's a type 2 error. Which one is which? The defendant is guilty, so that means null hypothesis is true or not true. So here this is null hypothesis is false, but the conclusion was do not reject the null, right?
Yeah, it was false because the null was that he was innocent.
Right, okay, so this is a type 2 error. All right, defendant is innocent. That would be the null hypothesis is true. And here the jury has rejected the null hypothesis. So the jury says guilty. And so this one is a type 1 error. Yeah.
When you're saying, when you're using these examples, the defendant is guilty and the defendant is innocent,
Yes.
does it really mean that they really are innocent and guilty, or are you talking about the system?
No. We're talking about, in reality, the defendant really is innocent. Like, this person didn't commit a crime, and yet he or she is being charged with a crime.
Oh, so that's a type 1 error.
Yeah, well, if the defendant really is innocent, didn't commit the crime, and for whatever reason the jury says guilty, we are sentencing you to life in prison, that is a type 1 error, okay? And on the other hand, there could be someone who committed the crime. Maybe the person actually did something bad, but because of a good defense team or whatever, the jury says not guilty, okay? And that would be a type 2 error. Now, we don't want to commit either of these errors, right? So ideally, every person that's guilty will be found guilty, and every person who's innocent will be acquitted, okay? But mistakes happen, and we have type 2 error and we have type 1 error. So, you know, this is a point, I guess, up for debate, but if we had to say one of these errors is worse than the other, which error would we say is worse? Yeah, type 1 error is worse, right? You know. So we can probably think of some high-profile cases that have appeared on TV that maybe fit type 2 errors and stuff, and there are certain things, and whenever that happens, you know, you'll have people on TVs talking about, you know, this was a failure of the justice system, and it's true, because we don't want to make either of these mistakes. But I think we would agree that a type 1 error is worse, okay? That sending an innocent person to prison, or, you know, possibly even executing an innocent person, that would be a very bad thing. So we would say type 1 error is worse, okay? And so if the type 1 error is worse, do we want to pick a large alpha or a small alpha? Okay, so so alpha is the probability of a type 1 error, okay? So if the type 1 error is worse, do we want a large alpha or small alpha? We want a small alpha to minimize our chance of committing a type 1 error. So we prefer a small alpha. Okay, and they actually say this in court. In court, they don't say use a small alpha in your decision making, but what do they tell the jury?
Beyond a reasonable doubt.
Beyond a reasonable doubt. They use the phrase beyond a reasonable doubt. They don't want you to just convict someone on a hunch, or just say, this person looked guilty, so we're going to say guilty, you know? They don't want that, okay? Yep, beyond a reasonable doubt. So they want you to be sure beyond a reasonable doubt, and that's what they mean when I say prefer small alpha, okay? So, you know, there's classic movies like 12 Angry Men, where they talk about this, and it's never revealed as to what actually happened, but beyond a reasonable doubt. Okay. So if the type 1 error is worse, we would prefer a small alpha. And if the type 2 error is worse, on the other hand, if a type 2 error is worse, we would prefer a large alpha, okay? So let me kind of give you an example where maybe a type 2 error is worse, okay? So, okay, so you can think of like cancer screening. Okay, and so the null hypothesis would be patient is cancer-free, all right? We live our lives under this assumption, okay? We live our lives assuming we don't have cancer, and it's only until we experience symptoms that we say, oh, maybe I should go to the doctor, okay? Because we're assuming that this is the case, okay? And then the alternative is that the patient has cancer. Okay, and then, so, you know, rejecting the null hypothesis would be coming to the conclusion. So rejecting the null means we think the patient has cancer. And then not rejecting, do not reject the null. That would be, we do not think the patient has cancer. Okay, so ideal situations would be if the patient is cancer-free, we don't think the patient has cancer, and if the patient has cancer, we think the patient has cancer. Those are the ideal situations. We have type 1 and type 2 errors. What is a type 1 error? So the type 1 error is the null hypothesis is true, but we reject it. So type 1 error is...
We don't think that he has cancer.
So we tell them they have cancer. And
Yeah, so type 1 error is like going on WebMD, right? You don't
basically have cancer.
you don't have cancer, but you come to the conclusion that you have cancer, right? So this is you do not have cancer, but believe that you do.
So the type 1 error is accepting the null hypothesis, right?
No, type 1 error is you've rejected the null, but the null hypothesis is actually true. The null hypothesis is actually true, but your conclusion is you reject the null, and that's a mistake, okay? And then a type 2 error is, I don't know why I changed to you instead of patient, but you do have cancer, or the patient does have cancer, okay? But basically the cancer remains undetected. Okay, and so here the null is false, but we did not reject the null. Okay, so which error is worse? Type 2 error is worse, right? This is definitely worse. Okay, and because type 2 error is worse, you know, we preferred a large alpha. Okay, and that's why WebMD is is very ready to say it could be cancer, right? Because they don't, you know, a site like WebMD wants to make sure that if there is a problem, you're going to visit an actual doctor and get the problem resolved. And they don't want to, they believe, probably rightly so, that falsely telling somebody that they're healthy when in reality that there's serious problems is a worse thing to do than to give a healthy person concern, okay?
So just, I'm sorry, because I'm kind of confused in this concept. So you say right now the type 2 error is worse, so we prefer a large alpha.
Mm-hmm.
Alpha meaning the probability of being cancer-free, right?
No, alpha is the probability of a type 1 error, meaning that you believe you have cancer when you don't actually have cancer.
Yeah, so being cancer-free.
No. When being cancer-free is the null hypothesis, okay? Alpha is not the probability of the null hypothesis. Alpha is the probability of rejecting the null if the null hypothesis is true. It's a different thing, okay? And so I mean, but WebMD has gotten to the point almost where it's like the alpha has been set so high where like you type in any symptoms and it's like you have cancer, you know, you're pregnant or something. When you type, the alpha is so high that people now almost disregard when WebMD says it might be cancer. It's almost like the joke, right? But then, like, if you're a woman, you're supposed to do like a monthly breast exam or something like that. And that kind of self-checkup is important, but it has a very, quote, high alpha in that, anything that could possibly be wrong will register as, you should visit a doctor, right? So, if you feel something irregular, you should visit a doctor, okay? And that's, and notice that, they say if you feel something irregular, it doesn't mean you necessarily have cancer. It just means you should go to a doctor where they're going to have more precise tests that don't have as high of a alpha, okay? So generally, and then when you visit the doctor, they might give you an initial screening, and then based on that, they might say, okay, we need you to come in for a full biopsy or something like that. And it's kind of a series of different tests, first with the highest alpha, and as you keep going, the levels of false positives go down and down and down until the point where they're quite certain that, it's a cancerous thing, okay? But because the type 2 error is worse than the type 1 error, we tell people to do these things that have relatively high alphas, where the false positive rate is quite high, okay? Okay, so that is type 1 error and type 2 error. Is that okay? All right, why don't we take a short break here? Or actually, I don't know. If I just keep going, we might be able to just finish early. Would you prefer that? Yeah. Okay, then I'll just keep going. Well,
Like, how high is the alpha?
I don't, I will take this as enthusiasm for the subject of statistics. That you just want to keep learning and don't want to stop, right?
It's just a late class, that's all.
This is the story of my life. Okay. All right, I want to talk about a few sampling methods. So now we're completely changing the topic here, and we're going to talk about sampling methods. Okay, so what do I mean by sampling methods? Okay, so as far as sampling methods go, what we will say is this is how we try to select a sample that will be representative of the population, okay? How we select a sample that we hope And so, because we said, in statistics, the big picture idea is that we are looking at limited data. We are just looking at a sample of data, and based on that sample, we're trying to make conclusions about the population, right? So, recall that, we look at only a sample. Okay, and so there are kind of four methods that are worth talking about. Okay, we have simple random sampling, which we have already discussed, but I'll talk about again so we can compare it. Stratified sampling. Cluster sampling, and lastly, systematic sampling. Yes.
But you know, like with polling, like with the primaries, right?
Mm-hmm.
So isn't time also a factor? I mean, you could get the demographics, right? But
Yeah.
then as you get closer to the event,
Yeah. That's important, and so really the polling is only an accurate could only be accurate of the current time. So you cannot look at current polls and expect to predict what happens in November. Okay, and you know, just like 6 months ago, we couldn't look at polls and predict what would happen today and things like that. So
it's time down.
yeah, so I mean everything is, you know, when you take a sample now, it's representative of the population now. Okay, and the population will change over time. Okay, and so so yeah, a sample now is not going to be representative of the population at another point in time. Yeah. Okay, but yeah, I mean that's, so sampling is difficult in reality, but I'm going to just talk about some of the methods that exist. Okay, so so let's talk about simple random sampling. Or SRS, okay? So we begin with what we call a sampling frame. Okay, and the sampling frame is ideally a list of every single person in, or every single thing or person in the population of everyone. So that's really everyone in the population. Hello. If your sampling frame has deficiencies, then your sample will have the same deficiencies. Okay, so if your sampling frame is not a list of everyone and is missing a certain demographic, then the resulting sample will have the same deficiencies. It will be missing the same demographic. Okay, so deficiencies in the sampling frame will deficiencies in the sampling frame will appear in the resulting sample. Will be present in the resulting sample. So you want to try to get everyone in the sampling frame, okay? And then what you do is you just select people one by one at random, individuals at random from the sampling frame, at random, one by one from the sampling frame. Okay, at random means use some kind of random device. Don't just pick them arbitrarily. Okay, random is not arbitrary. Okay, so use a randomizing device. Okay, So there's like there's a website called random.org, and it will, if you give it a list, it will pick things at random from that list. Okay? Or you could, you know, old-fashioned random methods work too. You could write everybody's name on a piece of paper, put them into a hat, mix up the hat, and then pick them out. Okay? Those types of methods work well, you know. But then people complain, like, right, like if you have a raffle thing and you put them in a big drum and you spin it around, people say like, oh, my thing got stuck on the side, so it wasn't going to get selected, you know. So, you know, physical random methods can have physical problems, okay, but in general, they're pretty good, okay. It's much better than just going like, here, and okay, because this is arbitrary. Picking, depending on yourself, to be quote random is not really random. It's going to be completely arbitrary, and you could definitely tell the difference between arbitrary sampling and truly random sampling. Okay, and the results will be all individuals have an equal chance of being selected. Okay, and then all possible samples have an equal chance of being selected. So if you think of like the lottery, okay, every combination of numbers, the combination 1, 2, 3, 4, 5, 6, has the same chance of being selected as the combination 2, 25, 37, 48, 52, 61, or whatever, okay? All possible combinations have an equal chance of being selected. That's what we mean by all possible samples have an equal chance of being selected. So that's simple random sampling. Good? Okay. With the next kind is called stratified sampling. In stratified sampling, the population is divided into subgroups. Called strata. Okay. Often these subgroups are based on kind of demographic characteristics. Often the strata are determined demographic characteristics, okay, and then so what happens is members of the strata are selected at random of each strata are selected at random so that the resulting sample has similar demographics as the population. Okay, so for example, if you wanted to get a stratified sample of the state of California, we would first have to figure out, kind of the demographics of California. So let me demographics. Whoops, spelled that wrong. Okay. And then let's look at Wikipedia and just see what this has to say.
So when they do like sampling for, you know how they make movies usually aimed at a certain demographic?
Uh-huh.
Do they use this kind of sampling to see, you know, strata sampling to a certain?
You know, I think when they choose to make movies aimed at a certain demographic, I don't think they're not trying to get like a random something. they're just trying to.
Reactions, you know, you go to the free movies, you know. Who they-
Yeah, but you know they don't. In general, when marketing teams for movies like that, like they're only interested in the opinion of that demographic that they're marketing to. Okay, so you know if there's a movie for you know a certain demographic, they don't care if these people who aren't going to spend money to watch the movie, they don't care about these people's opinions, right? Like if this group of people is the group that they're aiming for, they really only care about these people's opinions.
They don't care about the other ones in the same age so they don't like the movies. Did you see that? I understand what you mean.
They're not, you know. You know, for example, if a country music artist releases an album, okay, they're not going to ask people who listen to hip hop music to review the CD, because they just know that they're not going to like the music because this is not the group that they're. What they care about is the people who listen to country music, what they think of the album. Okay. Likewise, you know, if a hip hop artist releases an album, he or she's not going to ask people who listen to country music for their review. So as far as those things, it doesn't matter. But if, you know, if we're curious what, you know, overall, like what percentage of people are going to vote for a certain candidate, then we might want to make sure that the sample we select looks like the population that we're talking about, right? Because, you know, sometimes, you know, people, you know, their demographic characteristics will greatly influence or are very predictive of someone's behavior, right? Like, you know, in the media they say like young people are more likely to prefer this candidate, old people are more likely to prefer this candidate, you know, white people are more likely to prefer this candidate, and, you know, non-white people are more likely to prefer other candidates, things like that, okay? And so when you're trying to see overall what percentage of people are going to support a certain candidate, you probably want to make sure that the sample you're selecting has the correct amount of certain groups of people, right? Because if you get too many young people in your sample, then the results might skew a certain way, okay? And we don't want that. So basically with stratified sampling, you're saying, okay, I know these demographics exist, and I think the demographics play into the responses that I'm going to get. Therefore, when I select my sample, I want to make sure my sample reflects the demographics in the population, okay? And so, you know, here it says stuff like this, and it says, okay, well, we want to make sure that we get these matching demographics if we're going to select a sample, okay? Stuff like that. Does that make sense? Okay, so that's stratified sampling, okay? So you think, and it's not, I guess, in general, stratified sampling makes it even more work in your sampling because you're trying to aim for specific groups of people and things like that. So stratified sampling adds work to your sampling method, but it might be important if you believe, you know, these demographic things are going to play a part in the responses that you're going to get, okay? So that's stratified sampling, okay? on the other hand, we have cluster sampling, okay? So cluster sampling actually, so stratified sampling makes it harder to do sampling. Cluster sampling is in the hopes of making it easier, okay? With cluster sampling, so this is done to make sampling easier. Okay, and maybe I'll flip back to the other slide and say stratified sampling may be done to make it more accurate, to make sampling more accurate. Okay, but it is more work to do stratified sampling. Okay. Oops. So with cluster sampling, we're doing sampling this method to make it easier. So here, getting a true sampling frame, a list of everyone in the population, is hard work. Okay. It would be getting a list of everyone is hard work, okay? But in the population, subgroups exist. And we will call these subgroups clusters. Okay? And it's relatively easy. It's easier to get a list of the subgroups, or the list of the clusters. Okay? And then so with cluster sampling, we perform random sampling on the list of clusters. Okay, and then we either survey everyone in the selected clusters, or we perform random sampling within those clusters. Okay. Select everyone, or perform simple random sampling on the selected clusters. Okay, so here, this one I'll give you an example. So let's say you wanted a list of, you want to get a random sample of everyone who goes to church in Los Angeles County, okay? Get a random sample of all churchgoers in LA County. Okay, it would be very difficult to get a list of everyone who goes to church. Okay, so getting the sampling frame would be very difficult. But this population of everyone who goes to church is naturally divided into clusters of different churches. Okay, and it's relatively easy to get a list of all the churches in LA County. Okay, so where it'd be very difficult to get a list of every single person who goes to church, it's not too hard to get a list of all the churches that exist in LA County. Okay. So much easier. Okay, and so with the list of all the churches, then you would do a random selection of churches. Okay, so randomly select churches from this list. Okay, so maybe you select like 50 churches or something. Okay, and then with those 50 selected churches, then you go to each one and you perform random sampling. Okay, and then so, or you know, take a census at each of those selected churches. Okay. Perform random sampling. At the selected churches. Okay. Is that all right? So that's cluster sampling. So here we are just selecting a certain number of clusters out of the population, and then we do random sampling within the selected clusters. Okay, and then as far as the last sampling method that I want to cover is systematic sampling. So with systematic sampling, okay, this one's best suited for lines or queues. And basically you just say, we're going to select every nth person in the line, in the list, or yeah, in the line. Okay, so you know, maybe select every 9th person in line, okay? So you know, you're at the checkout. You know, select every 9th person in line. You know, at the airport, they always say, like, you've been selected for random screening or whatever. And it's most likely a lie that it's not really random, okay? But if they really stood by that, and they said if they really wanted it to be random sampling, they could totally make it truly random and it would be completely fair, and I don't think anyone would complain, is if they had like a dice or a die, and you just roll the die, and if you know, like they paint one of the sides red, if you get the red side, you get selected for random screening, okay? And you could have a 20-sided die or whatever if you only want to screen 5%, and then it would be completely fair, right? And nobody would complain. They'd just roll it and they'd be like, ah, crap, I got the red face, but then that would be truly random and no one would complain.
So
but
that little light on customs is not truly randomized? Or
yeah,
they check the cameras and then...
yeah, you know, I think we all suspect that that it's not random, right? That they're using certain other methods for selecting people, and you know, whether you know there's an argument that whatever, right? That non-random methods may quote unquote be, you know, better or not. I don't know. Yeah, I think in the United States, we're one of our principles that we hold fast to is fairness, or we prefer for fairness, and of course nothing truly is fair. But in other countries, they make no qualms about selecting people in a completely non-random way. But okay. Anyway, all right. So let me just spend a couple minutes kind of doing a very quick review of all of the formulas and stuff that we have made that appeared, and I think this will be helpful as far as completing the practice final exam goes. Okay? Yeah, question?
What is the next quiz going to be
It's going to be, you'll
It's
see,
gonna be like
there's a
this.
practice quiz. It'll cover the sampling methods and all of this type 1 and type 2 error stuff, okay? There's going to be no calculations, okay? Just type 1 and type 2 error stuff, sampling methods, okay? It'll be, yeah, okay, so let's kind of, so let me just list off all of the topics we've covered, okay? So between basically chapters 7, 8, and 9, we have had confidence intervals. Yeah, this is a review, okay? This is a review before you do your practice final, and then next week we will review the entire practice final. And then that'll be it. And then you'll take the final. Okay, so we have confidence intervals for proportions, one sample. Okay, and then we have hypothesis tests, for proportions, one sample, okay? And we didn't do confidence intervals for proportions, 2 samples, but we did do hypothesis tests for proportions and 2 samples. Okay, I'm going to just abbreviate these CI and HT, okay? Then we have confidence intervals for means, 1 sample, hypothesis test for means, 2 samples, confidence intervals for I'm sorry, should be hypothesis test for means, 1 sample, and then I got ahead of myself here. Confidence intervals, hypothesis tests, and then confidence intervals and hypothesis tests with 2 samples. Okay, so we've covered like 7 different things. All right, so how do you know? So the most important thing is knowing which one of these you're using. Okay, so when you read a problem, you've got to know, is this a confidence interval or a hypothesis test question? Is this for means or is this for proportions? Do I have 1 sample or do I have 2 samples? Okay, because if you mess that part up, then you're going to be using the wrong formulas and then everything's going to not work. Okay, so you know, I don't have a question that says which one you're going to use. Okay, you just got to figure out what it is because all of the related questions depend on that. So make sure you get this part correct. All right, so how do we decide whether it's confidence interval or a hypothesis test? Okay, so generally the way the final is set up is like I've got this paragraph with the information, you know, the data, the question, and the setup of the problem. And then I'll have maybe like 4 questions related to each paragraph, okay? And it'll be like, you know, what's the test statistic, or what's the upper bound of the confidence interval, or, you know, what conclusion do you make, or what's your p-value, or things like that. Questions related to that paragraph. So how do we figure out what's what? Okay, so if you have a categorical variable, okay, then you are dealing with proportions. Okay, if somewhere in the question it says proportion, you're dealing with proportions. Okay. All right. So, or if you see proportion in the question, then you've got proportions. Okay. All right, and if you have a numeric variable, then you're dealing with means, okay? Or if you see average, mean, or standard deviation, if there's a standard deviation in the problem, standard deviation is given in the problem, then you are dealing with means. Okay? All right, deciding if you have one sample or two samples, okay? Read through the problem and try to count how many n's you can identify. Okay? Let me see. I think I'm going to have to...
If you see the word proportion in the question, that's a
It's an indicator that you're dealing with proportions. Yeah. So I'm trying to. I can't think of. I'm trying to think. Okay. Yeah. Okay. So how many samples? Okay. Read carefully through the problem and see if you can identify how many n's you have. And try to identify n. Okay, if you can only find one n in the problem, then you've got one sample, okay? If you can identify two n's, then you've got two samples, okay? So, I mean, it sounds obvious, but students will... Huh? No, n is the sample size. N is the sample size. Yeah, n is the sample size, okay? So, you know, only one n, that's one sample. Okay, two n's, great, two samples. Okay, and then, all right, confidence intervals are hypothesis tests, all right? Confidence interval, there will always be something about a confidence level, okay? So if you see confidence level, then you've got a confidence interval, okay? Alpha, if you see, or if you see the word hypothesis in there, then it's a hypothesis test, okay? I mean, it sounds obvious, but these are the key words you're looking for, okay? If you see hypothesis in there, you've got a hypothesis test, okay? Okay, so once you figure out which one you're doing, then it's just a matter of like doing the same thing for all of these, okay? So I'm gonna do all of the confidence intervals first, okay? And there's three confidence interval things to do. And then I'll cover the hypothesis tests, of which there are 4. Okay, we ready? Next slide. Okay, so this is for all confidence intervals. Confidence interval stuff, okay? All right, so let's do confidence interval P1 sample. Okay, and so this is in the form P hat plus or minus Z star times the square root of P hat times 1 minus P hat over n, okay? P hat is the sample proportion, x over n, this is our sample proportion. Okay. Z star is our critical value, and there are 4 values you need to know, right? Okay, so we said 80%, you're going to use Z star is 1.28, 90%, Z star is 1.645, 95%, Z star 1.96, and 99%. Z star is 2.33. I'm sorry, 2.58. 2.58. 2.33 is 98%. Okay. Yeah, question.
So for the confidence interval, when it's p hat plus or minus z, it
Mhm.
can be z times se as well.
Yeah. So yeah, I guess, okay, so we'll say SE is the square root of p hat times 1 minus p hat over n, okay? And then, the middle of the interval is the p hat. And then the margin of error is always going to be your critical value times the standard error. So I'm going to just write z star times SE. Okay?
So I just want to know, you're giving us the formulas for each one that you just said. This is for
Correct.
the confidence interval.
Correct. Yeah, and I'll post a formula sheet online as well, okay? And then, so there's a formula sheet, and then I also have kind of like a guide for inference. Like, it's called the study guide, but it's really a guide for inference. And so, on the final exam, you're allowed 1 sheet front and back, okay? So you can write whatever you want. If you want to take the formula sheets that I've posted and use that as your sheet and then, write on the remaining space, that's up to you. I've seen people like take my stuff and then like shrink it down even super small and then like wrote on the back side. Whatever you want to do, okay? I think,
So it can be written on the computer type?
yeah, it can be on the computer and you can shrink down whatever stuff I've put on there if you want. You can just use it as well.
We can type it actually.
You can type it. You can type it out. Yeah. Just make your own thing. Make your own thing, yeah.
What's that last thing you wrote?
It says ME, margin of error. Margin of error is Z star times the standard error. Okay? All right, and then we have confidence intervals for mu, or means, 1 sample. Okay? And so this is x bar plus or minus t star times s1 squared over n1 plus s2 squared over n2, okay? What's that?
First, do we need to write all this?
That's for 1 sample.
This is for 1 sample. Oh, I'm sorry. I've messed this up. Thank you. I'm like,
Square root of n.
thank you. I apologize. Okay, everybody, I messed that one up. I'm not. S over the square root of n. Thank you. Sorry. 1 sample. Good catch.
So this is all printed out, right? We don't need to write this right now, right? Like it's
Yeah,
printed
you,
out, more organized.
whatever, if you don't want to take notes, you don't have to take notes. You don't have to write this up. This is going to be posted online.
Yeah,
Okay.
it's more organized the way maybe you posted it.
I don't know. I've got a formula sheet posted. You can look at it and you can decide if that's more organized than what the notes I'm printing here, okay? It's always my intention to present the notes on the screen in an organized fashion, so if you say, is your other notes more organized than the notes you're giving now, I don't know how to answer that. Okay, but thank you for catching this mistake here. Okay, so x bar is our sample mean. S is our sample standard deviation. N is our sample size, as always, okay? And then T star comes from the T table with degrees of freedom equal to N minus 1. And that's it. Okay? And then confidence interval for the quantity mu1 minus mu2, 2 samples. Okay? I mean, do I have to write the middle as x bar and the margin of error is... No, you guys know that, right? Okay. You want me to write it still? Okay, sure. Okay. All right. Standard error is s over the square root of n. Okay, and the middle is x bar, and then the margin of error is t star times s over the square root of n, or the critical value times standard error. The margin of error is always critical value times the standard error. Okay? All right, over here, x bar 1 minus x bar 2 goes into the middle, plus or minus t star times s1 squared over n1 plus s2 squared over n2, okay? X bar 1 and x bar 2 are sample means of your 2 samples. S1 and S2 are sample standard deviations. And T star comes from the T table with degrees of freedom equal to n minus 1, and you are use the smaller of n1 and n2. Okay, standard error is exactly what it is. Okay, in the middle is x bar 1 minus x bar 2, and the margin of error is always t, or critical value times the standard error. I don't feel like rewriting all of the standard error out. Okay, whoops. Oh dear, what did I do? Something unintended. Okay, so this was stuff for confidence intervals, the formulas, as far as the formulas go. Okay, and then looks like some of you are still writing, so I'll wait before I flip. And then as far as conclusions go, okay, you would say I am blank % confident that, okay, and you'd say, you know, either the proportion of whatever, or, you know, the mean height, mean whatever of whatever is between blank the low and blank the high. Okay, this is for one sample. If you have one sample, P or mu. Okay, so that's, you know, I'm blank % confident that if you, obviously if you had P, it's the proportion of, you know, people who have red hair is between blank % and blank %, okay? Or, you know, I am blank % confident that the average height of, I don't know, Tyrannosaurus Rex skeletons is between something and something, okay? And then it might ask, like, do you have evidence that the blank proportion or mean is not equal to some number. I'll just write some number k. All right, and then basically, if k is in the interval, no, you do not have evidence that it's not k. Evidence that, you know, p or mu, whatever it is not k, okay? And if k is outside of the interval, yes, you do have evidence that p or mu is not k. Is that okay? Should I do it also for the 2 samples means, or are we okay? No, it's just do it now. Okay, just do it now. We'll do it. Okay, you guys have all this written down? Okay, I'll wait. All right, okay. Okay, next. All right, and then, okay, so then if you have 2 samples, and so this is, you know, mu1 minus mu2. All right, we would say, you know, I am blank % confident that the average blank of blank is between low and between blank and blank more, you know, if positive, or less if the values are negative, then the average blank of, you know, so this is group 1 and blank of group 2. Okay? Do you have evidence of a difference?
This is how you do the conclusion?
Yes. Okay, and so if 0 is within the interval, no evidence of a difference between mu1 and mu2. Okay, and then if 0 is not in the interval, then you do have evidence of a difference between mu1 and mu2. Okay, some of you guys are still writing, so I'll let you catch up. Okay, and then, all right, so let's talk hypothesis tests. Okay, so all hypotheses have the same 4 steps, okay? Step 1, make your hypotheses, okay? And it's always important that the null hypothesis will always have an equal sign. And then the alternative will always be identical to the null, except the equal sign is something else. Is not equal or greater than or less than. Okay? Step 2 is check your conditions, which we are not going to have you do on the test during the thing. There's a separate section where it's like check your conditions here. Okay, kind of like on one of your quizzes, we had questions that said check your conditions. You'll have that. Okay, but as far as the actual problem, I'm not going to have you check conditions in that problem. Okay, check conditions and select alpha. So step 2 is kind of understood to be done for you in the thing. Okay, step 3 will be calculations, and the steps can always be kind of broken down into 3A, which is get your standard error, 3B, which is get your test statistic, sometimes it's better to not say anything and just pretend like you don't know what's happening, right? Now you've outed yourself. Test statistic, and then lastly, look up the test statistic to get your p-value. Okay, so the calculations, that's step 3, and then step 4 is your conclusion. All right, and the conclusion is if the p-value is greater than alpha, do not reject the null. Okay, you do not have evidence to support the alternative. And if the p-value is less than alpha, reject the null. Okay, you can say accept the alternative, and you do have evidence to support the alternative. Okay, so all of the hypothesis tests, there's 4 different tests. All of them kind of will fit this. So I'm really just going to focus on basically step 1 and step 3 when I talk about the different hypothesis tests, because as far as the conclusion goes and checking your conditions, those are pretty much set. Okay, so I'm just going to talk about step 1 and step 3. 3A, 3B, 3C on the next slide here, okay? Cool. All right, so we got hypothesis tests for proportions. I'm just gonna write for P, 1 sample. Okay, and I think that looks about halfway down. All right, so your hypotheses, your null hypothesis is P is equal to some number P0, okay? Now P0 is like, is a number, like 20%. And then the alternative is P is not equal to that same number. So for example, you got p equal to, the null hypothesis would be p equal to 0.3, and then the alternative will be p is not equal to 0.3, okay? And then your standard error is the square root of p0 times 1 minus p0 over n. So this would be 3a. Your I'm just going to write standard error. Okay, your test statistic is z is equal to p hat minus p0 divided by the standard error. Okay, and then you look up z in the z table. Okay, is that good? All right, hypothesis test for P1 and P2 with 2 samples. Okay, the null hypothesis is always going to be P1 is equal to P2, and then the alternative is P1, you know, not equal to P2, okay, or less than or greater than, okay. So in all of these examples I'm just writing not equal, but it could be greater than or less than, okay, of course. All right, and then so here you need to figure out your overall p hat, which is going to be x1 plus x2 over n1 plus n2. Your standard error is, once you figure out p hat, is going to be p hat times 1 minus p hat times 1 over n1 plus 1 over n2. And then your z, p hat 1 minus p hat 2 divided by the standard error, okay? And then look up z in the z table.
So the Z table and the T tables are also, you can still print them out on the canvas, right? It's all there? Like if
They're available for download and printing on chapter in week 5. Okay, so I gave them, so in week 5 I handed out the Z table, the binomial, and the T table. They're all kind of together. And so on Canvas, you don't need the binomial table anymore. That's done. Okay, so you just need the Z and the T. Okay, but they're available for you to download under week 5. Okay, we'll just keep ticking along and then we'll be done. Hypothesis test for mu, 1 sample. Null hypothesis. Mu is equal to some number mu 0. The alternative, mu does not equal mu 0. I think I'll take attendance when I'm done, so don't just up and leave. So, okay, just a heads up there. All right. Standard error, s over the square root of n, and your test statistic is t equal to x bar minus mu 0 divided by the standard error. And then you'll look up t in the t table with degrees of freedom equal to n minus 1. And lastly, hypothesis tests for mu 1 and mu 2. And you've got 2 samples. We've got the null hypothesis, always mu 1 equal to mu 2. The alternative, mu 1 not equal to mu 2. Okay, and of course, you can also have mu 1 as, null hypothesis, mu 1 minus mu 2 equal to 0, right? And then same over here, p1 minus p2 could also equal 0, okay? But these are saying the exact same thing. There's absolutely no difference between those. Okay, the standard error here is going to be s1 squared over n1 plus s2 squared over n2. The test statistic t is x bar 1 minus x bar 2 divided by our standard error. and then you're going to look up t in the t table with degrees of freedom equal to n minus 1. Use the smaller of n1 and n2. And that's everything, I think. Okay. All right. I'm going to I'll stop here, and then I'll take roll, and then you guys can go.